Okay. Good morning, ladies and gentlemen. Warm welcome from my side at Luleå. We are starting the Mine.io workshop. It's a pleasure and great honor to have you all here and the guys that are joining us online. My name is Marek Kościelski. I'm representing Łukasiewicz ITR, and together with me on stage is
Jan Emi from Luleå University of Technology.
And we will try to get you on board with what we have for today. So our agenda is quite packed. We have 4 technical speeches that will follow. We will give you some introduction on the project itself. Because of some hiccups, we will have to switch again because the weather here is, we have chilly -5 with a bit of wind. So we have to change a bit the plans, so the opening will be done by me and Jan here. Other than that, we'll follow with the agenda listed here. Some rules about the housekeeping, so we will give you the presentations for download available on our site afterwards. Other than that, let's move on with the presentation. Just a few facts in a nutshell from the Mine.io project. As you can see, we are quite well scattered around Europe. We have 25 partners around Europe and 7 use cases altogether, where basically we are applying the technology that we are working on. The budget of the project in total is 14 million euros, and the duration of the project itself is 42 months. When we look at the vision of the project, so as you can see, the idea behind it was basically holistic digital mine. And what we mean by that is basically industrialization and informatization, and together with that, it can be also connecting, because we are also tackling sustainable development. When we go into details, what's quite crucial here is basically we would like to focus on a novel mining digital ecosystem. What we mean by this is basically a platform that we will be able to feed the data from different resources. And we will cover that in one of our presentations. What solutions we are embracing is basically we are, one can say, focusing from cradle to the grave. But in a mining scenario, so we are starting from the resource exploration. We are moving to the extraction processes, and then basically also waste management. And some of those topics will be also covered within today's workshop. When we move on, here is the draft idea that our pilots are covering. Today we'll tackle only the 2 ones on the distance on the left, so the Portuguese and the German site. In the Portuguese site, we'll cover and tell you more about the underwater rowboats and connected with Dan Mions. Then we move on to Germany with AI and the platform itself. And what's next, we will cover the things that are connected on the far right, so waste management. All the things that are connected in the middle, that's a sneak peek we will probably cover in the next workshop, so bear with us, join us in the next workshop that will come. I think then I will move on to Jan.
You can keep. Maybe I can continue to say something about the pilots that we don't cover in this presentation, so to say, is the first, the Pilot 5, which is the Oberwiesenthal AFS mine in Germany. And we are talking about electrical charging of autonomous vehicle underground trucks. So we are talking about there where we, so to say, wirelessly charge the trucks and making them autonomous. So the goal is to have, in the future, of course, 24/7 trucks going around in the mines. And in the Polish one, in KGHM, we have this optimization of the flotation process, where we're going to use machine learning and AI for optimize this process. And then we have the other one in Freiberg is the smelter, where we're going to put in some new sensors and build a digital twin based on the new sensors also to control and optimize the smelter. Don't know. So this is a very brief introduction to what we are going to talk about today. The first presentation will be on sustainable exploration, a new paradigm, and where we will talk about how to combine the muon sensors together with an underwater vehicle. And if you don't know what the muon sensor, Mario will tell you about what that is, so you know, don't worry about that. And in this case, we are looking at the exploration in flooded mines. So it is in old field mine, water-filled mines, in this case. And yeah, you will see it later on in Mario's presentation. The next presentation will be environmental management, advanced risk assessment, where Vasileios will talk about how they monitoring their stockpiles and waste in the old historical mine in Luleå, and how these measurements can help them assess the risk with this and mitigate the risk and enhance their safety protocols.
It's on.
But not there.
Yeah.
Okay. Then we have the environmental management also again, and this time we're talking about reliable surveillance operations. And this is Raul from Oulu will talk about this in the Finnish mine in Pyhäsalmi. And he was talking about how they monitor the tailing dam and how they can enable early risk detection and ensure reliable operations with it. And he will also talk about the huge amount of sensors they have drilled down in this tailing dam, so they can monitor this. There are different types of sensors. He will go through that also. And then the last, after the lunch, we'll continue with this presentation from Dimitris and Max, where they will discuss the MineIO platform and how they digitalize this platform, the digitalization of the platform and digitalization of the drill rig in the Friedemann mine. And the idea with this platform is to help the mining industry to efficiently collect and integrate and analyze the data in the cloud, so to say. And then we have the drilling machine where we go, as an example, how we can do this can work. So we will talk about this drilling machine with a couple of sensors where we can have doing the analysis like a measurement while drilling, predictive maintenance, and so on in that mine, so to say, in the drill rig. And the data from the platform will be then sent back to the operator so he can see what's going on, or the manager, so he can plan the predictive maintenance of the equipment. And this is all partners, so to say.
Yeah, those you have listed all the partners that participate in the project. When we come to one of the last introduction and slides, we will try to be as interactive as possible, especially with you guys that are online with us. So we prepared a Mentimeter code for you. You're supposed to have that online in your email boxes, but you can also scan it here. So basically, we would like to feed you with some questions after the presentations, but also we have quite good coverage with our technical staff connected with you guys online, with Paul-Erik and later on with Katerina Margariti. So if you have any questions, post it in the chat. We will try to answer them during our last entry, let's call it this way. After the lunch, we have open discussions. So basically, all those questions can be answered there. Also, if we will not manage to answer your questions or we will miss it, please stay with us, and basically our specialist will manage to answer it afterwards, because some of the questions might be quite lengthy to answer. Without further ado, I think we can move to the technical presentations and to move one by one with I would like to welcome on the stage Mario, and he will just give you some insights on muons. Mario, the stage is yours.
Hello, everyone. I'm Mario Arancibia. I'm part of Muon Solutions, and my team partner, Paula Lima, which will join us later. We prepared this presentation about sustainable exploration, a new paradigm. So, basically, we will show how the new underwater or subaqueous exploration methods, specifically using muon detectors, will transform how we explore the critical resources, right? So these innovations will be more efficient, more accurate, and also with this comes together the reduced environmental footprint of exploration activities, right? So the benefits and impact we believe that it will impact the exploration industry positively by reducing the cost, time, and making everything more efficient and more sustainable, right? So I'm going to talk about muons. What are muons? Well, muons are regarded as heavy electrons, similar to electrons, but with more mass, and they travel close to speed of light. They are generated in the upper atmosphere, and they go around the surface of the Earth all the time, and they go through all materials, right? So there's a constant flux of particles all the time, and we were able to measure these particles, right? And the difference of muon flux through the different materials. So as they penetrate all materials, as you can see down here, the more dense the area, the less muons that pass through, and the less dense, more muons pass through, right? So using this principle, as you can see in this image, we can set up muon detectors in different places, and we may expect, for instance, the one that is deeper, and the muons will cross through more dense material in the bottom, and we also have some muon probes that are set to be used in drill holes. Is the one that you see in the middle, right? So we use these drill holes to put these muon probe detectors. So at the end, what does this technique is to map the density distribution in the Earth, in this case, in the rocks, and by measuring the difference in muon flux through density. So how does this look? You can see in the upper image, there's a polar plot of a muography, and you can see that this red straight line, it reflects a tunnel, right? So there was a more muon flux through this area, which reflects a tunnel in this case, right? This was done in a mine, and you can see how it looks, a muon telescope. And the other image, it's a muon tomography survey, which we will touch later on. This specific survey, right? So when we talk about muon imaging, we talk about myography, right? So as a technique, the myography utilizes muons to image internal structures of object by detecting the density variations in the medium, right? As I explained briefly. So image objects can be as big as pyramids or volcanoes and as small as few meters in across. Why do I put these examples? Because these are applications that were done in the past and are done currently. So they have been able to image through pyramids in archaeology and volcanoes also. So it's a safe method, right? As the muons are generated in the upper atmosphere and they cross through, it's a passive method. So there's no man-made geophysical fields, explosive, and this is a method that is conventional to other geophysical methods. For instance, gravity or seismics. So how can we apply myography in mineral exploration and mining? Well, one application that it's quite useful is in target discovery. As you know, in exploration, there's a limited amount of resources devoted to target discovery and drilling, right? So by having a sense of a more dense area that may be related to, let's say, ore mineralization, as you can see in this drill hole, you can see the sulfides have a higher density than the rock with sulfides have a higher density that the surrounding rock, can lead to better define where do I want to drill, right? But also may have another purposes. For instance, we know that there's a difference in density among two rock types. It can be used for lithological characterization, right? Also structural mapping. Let's say we have a fault zone and a damaged zone infilled with clays, hence a less dense medium. I would expect more muons to pass through, or the opposite, right? And lately in mining, let's say a mining development, when talking about an operating mine which works with block models and a lot of certainty into what's in each area, we can improve the certainty by combining this myography, all this information I give you briefly about lithological characterization, structural, and rock types and minerals by making the model more accurate. So this is an animation of a real myography survey done in a mine, in Saxor mine in Germany, and there were 2 points, right? You can see 2 cones, 2 inverted cones, which are the observation points, and the colors reflect difference in density. So you can see the light blue and the pink. Those are comparable differences in density, right? So we need to feedback with the geological team if this makes sense to them and can easily reflect, for instance, I'm not saying this is the case, but for instance, can reflect 2 rock types or a mineralization and sterile rock, for instance. And that red is the shaft, right? So it's a less dense area, which we access through to put these 2 observation points. Why does it look like an inverted cone? Because as it's a telescope, it images, and we just go and look above, what's above us. Now going to what we will do in Mine.io, which is myography in flooded mines. We know that closed mines represent a big opportunity to exploit resources and explore what's left behind. You know that with the advance of mining and so all the The recovery technologies have improved. What before was not economic now can be economic if we recover it, right? So there's a lot of potential into going into a mine and see what we can recover from it, right? So for instance, in a flooded mine, it's a challenging environment, right? So we intend to perform a myography in a flooded mine. I will explain you how we plan to do it. And of course, by doing it this way, we comply with the coefficient technological solutions that we are aiming in Mine IO. Okay, more or less the plan is to locate the muon detectors in this open pit. You can see the water level, and in pink you can see more or less how the myography will see. And what we expect to see is in the borders, we put a fault zone, for instance, that we can track, or we put a void that can be also a geological feature that can be reflected by myography, by difference of density, as I explained before, right? And this will be placed in the specific sites we decide by an underwater vehicle. And this will be done in the Malaposta open pit in Portugal. Okay, this is the muon detector we planned. As you can see in the upper left, that's the original plan. How will it be the vessel that will contain this muon detector? Then you see the fabrication of it. And this will be sealed and can operate underwater, right? So in this graphic, you can see that it performed accurately by measuring in sealed mode. And now, this is recent photos. Our partners in Wigner Institute in Hungary, they were able to confirm the first long-term seal measurement in a water container. So that's how the measurement looks like. So we are refining this device to actually use it on the pilot site, right? So now changing a bit to another topic, which is the underwater vehicles and the pilot site that this will be tested. Okay, this is the pilot site number 6 in Portugal. So we see that this will be in Malaposta open pit. It will be the test and validation of the underwater muon telescope, as I showed you before. And the EVA AUV, which is autonomous underwater vehicle, will transport this muon detector and deploy it and then recover it. In the pilot site 6.2, there will be an underwater vehicle for in situ exploration in flooded mines, which will be in Malaposta and also in Urgairica. And this robot will be used to scan and map with precision the underwater surface, right? So I will go into the details of the AUVs, right? So this is the EVA, is the one meant for putting the muon telescope on place, transport it, deploy it, then recover it, right? So we have a specific task in a work package to perform this, and you can see some specifications of this ROV, right? It has autonomous navigation, and it has been used in multiple sea deployments for inspection and mapping applications by our partners of Inestec. So again, we're in Malaposta open pit, where we intend to test this rover and the muon deployment. So Malaposta is a gneissic quarry used for rocks, right, for rocks extraction. And actually it's a flooded pit, but it has some benefits that makes it for us to be a good candidate to test this, as there's a ramp with access to water, possible local storage facilities, electrical power generation available, 4G communications, and there's a partial aerial LiDAR scan of the environment. The Urgairisa mine, it's another mine that has a main shaft, and also has good conditions for testing the rovers, right? The control room is quite close to the shaft entrance. There's fiber optic infrastructure, power, internet communications, and there's a deployment winch at the shaft, and the water level is around 7-meter depth. So all these benefits the test of these technologies. Now we are going to the second underwater explorer, which is the UX-1 Neo. It has all these specifications, right? I won't get much into details, but this one, it's meant for precise underwater navigation and scanning, exploring, right? You will see the scale, but it's smaller in size, and it's meant for a more fine job, if you want to call it that way. So you can see on site, the data can be deployed in real time during the dive. And you can see some of the UX-1 Neo cameras and the precise mapping it has. There's a video stream of it, right? So this is more or less how it looks with the different cameras. So the intention of going with this is to see if there is any unseen, then you see really what's in there before going with more equipment or so. So you can see it can produce fine photogrammetry in this case. There's another example of the shaft in Urgairisa. And you can see that some mineralization examples were scanned by UV light. You can see in the right image how the mineral in the rock it's shown. And another thing is that it can navigate untethered, so can go with the motors without a cable. That's what it means. So this is the UX-1 Neo. So the Neo Underwater Explorer has new autonomy capabilities. There's an optical link to it. And that will be the presentation. So as you can see, the intention of this exploration using rovers and muon detectors is to try to go with something new, to go for resources in difficult to access areas using all these navigation rovers, and this new technology where we don't need somebody who is constantly controlling what's in there. We just put the devices, and worst case, there's no presence of people. So it's also a safe technology. So we can now go to Menti. If you have you can input your your answers, so we can go to it. Right?
Okay, Mario, thank you for the presentation.
Yep.
The next slide will be on few questions that will be asked on Menti, as
Yeah.
Mario just said. Again, thank you for revealing some background about the muons and some things about the physics on particular matters. We can start with questions here. Next slide. Yeah. Here is the first questions that crops up. Do you want to read it out?
Okay, so first question is, do you know how many years it takes on average to a project transition from discovery to an operational mine, right? So you can choose among these different options. Okay.
We will wait for the answers to pop in. So
everybody can participate. So.
Okay, some numbers are still coming, so we got some input. Comment right away, Mario, from the input that is already here?
The thing is that once you hit mineralization, let's say, you are seeing only through a fine finger, and you need to expand it to the sides. So we say, okay, we have something here, to the sides, to there, okay, something significant. We make the economics, can be worth to extract it, I don't know. Then from this point, so when it becomes a business and an investment and an infrastructure, engineering, etc. Right? So there is. Okay.
Can we move to the other question then?
Okay. So see that most of you said among 15 years or more than 15 years, and that's accurate. Usually it takes more than 16 years in average once we know that there's a deposit, right, to convert it into a mine. Usually it takes longer than that due to other factors, social licenses, economic variations or so, but on average, worldwide, taking all projects, it's 16.4 years. Yeah, so most of you were accurate on this one.
Well, 15 is also quite close, so.
Yeah, of course. 1 year. Okay.
We can move on till the next question?
We can move on to the next question, right. So
what is the question?
What is the success rate of exploration, right? So that means amount of early stage projects, let's say we're going to explore this region, that end up in a new discovery of a new deposit, new mineral resources. So what's from all the projects, how many of those, if we put it in percentage, how many of those result in an actual discovery? Doesn't matter if it goes to a mine, but we find something that may be valuable in the future. Now, we don't know, but the resource is there. Okay, so see people is participating.
Yeah, 16.
Quite interactive. Yeah, some even change their criteria.
Yeah, waiting for the other people to join. Maybe it will have a decision vote here. Democracy. We'll see how it works.
Yes.
Any more votes we will wait for in the meantime?
Yeah, people is still voting.
Yeah, but right away, what about those two comments? Less than 1% and 5% without revealing the real results. How would you judge them?
Yeah, well, let's see. Okay, so it says we could show the correct answer, and we expand a bit more about it.
Yeah, then we will close the voting now.
Okay. So, sadly, the truth is that less than 1% of all the exploration projects end up in a discovery. So, the exploration business, you need very optimistic people, because most likely you will not find anything in all your career, right? But it's the way that knowledge develops, you learn what to do, where not to drill, what to look for. But yeah, it's usually, but you need to invest. It's the only way to get new resources, to add new resources. But the success ratio is quite low, like 99.5% of the exploration projects don't success, right? So you need to be very optimistic. But of course, the more you try, the more chances of success.
Yeah.
And okay, so do we have more Mentimeter questions?
How about?
Okay, yeah, that's why do we bother to study all mines? This is like you need to. It's like an open question. You need to
drop your comment and basically input something.
Why do you think we are focusing into studying all mines to see what resources are left there, and also consider the background we just talked before, right? And all the aspects, economic, social, environmental, etc. So what do you think? So there was there were words to select, is it?
I'm not so sure how we focus on the questions, but still waiting for your responses. So be brave and input your responses. We are waiting for some.
Yeah, there's one response.
There we go. Brave guys.
quite accurate. You can go commenting. That's true. Better recovery tech. Actually, a big business is to go and see all tailings, all dam sites, where it's old material from old mines or ancient mines, if you like you have here in Europe, from very ancient times, can be an economic resource, right? Yeah, all here I see here is quite correct. Not fully exploited, where you know that there is a resource, a deposit. The most likely that if you drill next to it or you explore next to it, you can expand it at some direction, right? So I see all the words put here that are quite accurate. Yes, we need more resources. That's quite an important one. Also, you need to think about, I'm not a specialist in this topic, but there's also the social licenses, right? So you can revitalize the economic sector of a, let's say, abandoned town that usually lived on the mine by reactivating this mine and giving people more opportunities to work on this. So that's another factor. Plus, each time it's more difficult to open new grounds for, let's say, build a mine and having everybody happy, if you want to call it that way, by trying to communicate, hey, we're going to open a mine here. Are you okay with it? Yeah. So that's more or less the focus on this. But all of these words are absolutely accurate.
What about if we have already a locked value in them? So the locked value in the minerals and the economic status of the value of the mineral changes on the market.
Yes.
So what you already mentioned, we have a existing mine or a abandoned mine, and we can, how it is with retrofitting and muon detectors in that space. Can you elaborate on that?
Yeah, what we can say about this technology is that, okay, we know that mineral has these characteristics, if you want to say it, this density, this rock type, and if we just find that in an unexplored site, there's highly likely possibility of extension, then we confirm by drilling, okay, there's a lot of resource, change all the economics of this place, and it's up to the engineering to determine if, okay, it's worth to take it, it will add this amount of cash flow to the project, it's totally worth to recover it, and in this case, in the mines that we will try this, are flooded mines, right? So before going to invest a lot of money, okay, we can see in the underwater what's in the walls, for instance. If there's a geological fault, for instance, may not be worth to perhaps expand the pit, may be dangerous. Also geotechnical conditions, right? So it has a lot of value to know beforehand what is the rock like, how it should behave. It's what I expect. It's not worth to invest here, rather to go to this other place, right? So it's also cost-efficient tool, right? I think there was another question in the Mentimeter.
Maybe just one comment from my side.
All right.
You also, I know that you have not pinpointed here about the timeline of the muon detector itself.
Okay.
So
Yeah,
can you elaborate on
That's a good question. Yes. It depends a lot on what we want to, what's our target, right? So usually you can get very fine, high resolution imagery, muography, right? That can reveal perhaps tunnels, their straight direction and the angles and so, or the specific shape of the mineralized body, if you want to call it, right? But if we are in a stage that we need to compare rough densities, that we know this is a sterile rock, this is a highly likely mineralized rock that has, let's say, this amount in difference of density, just that we can see that contrast may be enough for that purpose, right? But in matters of time, it depends on the depth, right? Because as we go deeper, we get less muon flux. So if we want to have a same quality image at 200 meters, okay, we will need to expand the time of exposure, right? Usually, depending on I don't want to say like strict numbers, but takes from weeks to months, depending on the target that we want to image, and of course, the density of the surrounding rocks, and the geological environment, that is it, and of course the depth. Usually this technique is effective up to 500 meters depth, but we need, of course, more time to acquire the image. This technique works quite like a radiography, like X-ray radiography, right? So you expose the muon detector to the particles that are crossing it, and you see the density contrast.
Okay, you mentioned the depth, so right away the question comes up, what about the area? You showed us that there is a cone structure, so what area coverage do we have achieved through muon telescope?
Yeah, well,
of course, it's depending on the depth, but can you also point some figures here?
As the muon detector, remember the image I showed you on the Saxor. Perhaps we can go back to this if it's more clear, but it's an inverted cone, so we need to be below the target we want to image, right?
Yep.
So but we can vary the angle, right? So it forms like a cone, and like we can open the cone, and we extrapolate it with other observation points, and then everything is merged to create something that creates a 3D muography. But of course, the more points we can take, the best for having more accuracy.
Okay. I don't know if we have additional questions from.
We have one from the chat.
Yeah,
Actually.
okay.
We can take it now since we have time. Okay, regarding this flooded mine, there was a question about how to do the feasibility analysis in the underground mine, which is filled with
Sorry.
feasibility analysis. This one.
How to do feasibility analysis in underground mines, which is filled with water? Well, I'm not an expert in this topic, but my take as a geologist, I'm a geologist, you need to always drill to make sure that the resource you are measuring, right, and it's validated by, let's say, the market or is a valid resource. What the myography as a technique can help you is to say, okay, I guide you to go to this site. Now you need to drill it and do all the engineering to take the water out, etc., to see if it's work. It's a more complex process, but of course, by using myography and this technique can lead you to saving a lot of money. That's the goal of being efficient.
Yeah, so basically answering and developing on your answer, it's basically pinpointing the places that you still need to do some drilling, but it's quite specific, showing the area that you're supposed to do the drilling.
Exactly.
So you are not blindsided, as you showed the numbers of one of the first questions of the success rate of the mine, but you are pointing the geologist in the right direction, well to drill, and then there is their job of analyzing the value from the drill core.
Yeah, exactly. Making best use of the drilling resources, and you can quickly verify if, let's say, you pinpoint to a sector that has low potential, then you verify that the density is homogeneous, then you just make few drills to, okay, verifies what I saw with myography, for instance.
Perfect. Do we have any
other question from
I have.
Yeah, sure.
Now we are talking about doing the measurement in old mines, so to say. What about doing it in drilling a hole, and then you do it on so to say a fresh exploration?
Yes.
Is that possible to put them in a hole?
Yes, we have a drilling probe that is meant to go in a drill hole, right? So the intention of this is to measure in, let's say, certain depth, use the same hole as a place to put it, but as the muon detector is different in size, right? So we need perhaps more time of acquisition. It's not the optimal telescope, but it works. We have had some tests by using this. We are improving the probe technology. But yeah, we are working into this, and it, of course, will be interesting to see, because it's easier to access with a small hole rather than having these big tunnels that are not available in any place, right? But yes, we are developing this and it's working, yes.
Very nice question.
Yeah.
And basically pinpointing again for the next drill core. So you can drill and have additional information from the next spot and basically move your telescope to the next shaft, let's call it, or just a drill hole, and basically additional information, gather additional information.
Yes.
So
I mean, as a geologist, having like a preview of what's in the next corridor for saying before drilling, it's quite useful information, because it gives you a preview on what you might expect, right? So in the same case, if we see that we can cut the drills before, if we see that everything is homogeneous, as it was showing the myography, right? So, or we can see voids that can lead to difficulties in, let's say, constructing the mine that we did not see before, right? So it has a lot of applications. As long as you have density contrasts in the rock mass, you may be able to see it with mimeography.
Perfect, Mario. Maybe we can end this topic here and move on to the next presentation.
Right.
Thank you.
All right, thank you.
Yeah, a round of applause. That's true. Now on stage, I would like to welcome Vasileios, and we'll hear about risk assessment. So, Vasileios, the stage is yours.
Hello, everyone. My name is Vasileios Protonotarios. I'm a chemical engineer coming from Lavrion Technology and Cultural Park of the National Technical University of Athens. Lavrion is one of the pilots that are participating in this very ambitious MineIO project. And here we are going to have a small presentation of risk assessment approaches with respect to the technologies that we implement in our pilot. I have prepared this presentation in collaboration with the University of Salamanca and Axeligence were the technical, let's say, partners that supported us in the monitoring operations during our pilot implementation. First of all, we have to know what we are talking about. Here, we are dealing with mining and metallurgical waste, so it's very important to understand what are the main types of this waste and how they are characterized in terms of their hazardous potential. We are talking about tailings, we are talking about waste rock, and of course, slag as a byproduct of thermal metallurgical processes. And of course, it's very important to know that what are the main features, the main attributes of the metals and the other toxic elements that are contained in those wastes, so as to be in position to make predictions and assessment approaches. Some key environmental risks associated with the management of mining and metallurgical waste include, of course, water contamination, especially in the form of acid drainage, because the majority of this type of waste have a very large acid potential. Of course, soil contamination, because most of them are deposited on earth, on soil ground. Air pollution, when these pollutants are becoming airborne because of the prevailing winds. Biodiversity loss, because of all the above that may happen, and they may endanger ecosystems and humans that in and around those areas. And of course, some geotechnical issues regarding tailings and embankments, such the one that we have in Lavrion, failures that may happen due to collapse of these specific structures. And also a quick view on the regulatory framework and compliance regarding the waste, the mining and metallurgical waste management. Of course, it's very important to have assessed the environmental and social impact assessments related to our approach. And of course, all these assessments before any intervention is made include also a detailed plan for the close and the reclamation of the mine. and a very large portion of resources is also given to assess the social impact, as also my colleague Mario referred before, as a very important parameter for the successful operation and installation of a mining and metallurgical site. And of course, there is a strict framework with permits and licensing, especially in European countries, a lot of regulations that the mining and metallurgical companies and those that are dealing with the waste after have to follow in order to be in compliance with the European and the international law. So, talking about our site, our pilot site in Lavrion is a unique project realized by the National Technical University of Athens in the historical mining site of Lavrio. The history of Lavrion starts from the ancient Athenians and has been a place of large-scale mining and metallurgical activity for almost 3,000 years before, participating also in significant phases of the Greek and Athenian history, funded, let's say, the famous Athenian fleet during the Persian Wars. Thousands of years later, in the same place, the first industrial complex of the new Greek state after the Ottomans' occupation was founded by the French mining company, which ceased operations almost 35 years ago, by the end of the 80s. Lavrion is situated in the southern part of Attica Peninsula, almost 62 kilometers of the center of Athens. It's very easily acceptable from the airport and the center of Athens. And the project of rehabilitating both buildings and land in this area of almost 200,000 square meters of area was, first of all, to rehabilitate the buildings to the way that they are pictured before. And, of course, our main concern was the environmental interventions, because, as you can imagine, an area of heavy metallurgical and mining activity for more than 150 years, not including the ancient slugs and waste. The environmental problem was huge, so a serious and unique environmental intervention has been taking place in Lavrion, including the hazardous waste landfill, the waste repository that we're going to examine in this workshop, an underground hazardous waste space where specific type of wastes are deposited in a safe way in closed barrels, and also the decontamination of specific buildings with high archaeological value, but with a lot of static and pollution problems, like the one that you can see here, which was used as an arsenic backhouse, a big arsenic backhouse. Those projects were unique for the area of Lavrion, for Greece, and especially for Europe. Here is a view of the polluted soil repository. We call it dry tomb. You'll understand why later when you see the layers, because it's totally isolated. The pollutants and the waste are totally isolated from their environment. And you can also see the areas of excavation and the dry tomb in the left part of this picture. In the right part, you can see the top as it is now. It's difficult for someone to say that below this green layer there are hazardous waste. Here is some view of the continuity of the works during the construction of the site. Ex situ, because the waste were transferred in the repository, but on site because we have constructed the repository within the borders of Lavrion Technology and Cultural Park. So here we can see some numbers at last. You can see the average metal concentrations of the waste deposited in the landfill site, in the repository. You can see that the numbers are thousands of times greater than the limits for industrial use of the area, especially for lead and arsenic. And in the right part of the slide, you can see a 3D view of the different layers, a sandwich philosophy of the waste between different protective layers. So those layers are following a specific philosophy, starting from clean soil, geotextiles, drainage layers, a very low permeability polyethylene membrane, and of course an artificial geological barrier before as the last border before the waste. And of course, the same philosophy was followed for the bottom layer and for the sides of the site. So, in that case, we have the dry tomb. So, what was, how we're going to connect the risk assessment philosophy with what we have done in Lavrion and the construction of a repository. If you can see here, with a quick view in the relative costs of soil remediation methods, everybody almost in the field knows that they are very expensive methodologies. But as you can see, the most economical one and the most viable in our case with such a portion of waste was the excavation and the containment, the dry tomb method. Any other method, we have calculated that it would cost 3 or 4 times more, and with a significant increase in environmental impacts from the method that we choose, the method of the dry tomb. Here are some main features of the repository. You can see that the cost was amount to 27 euros per ton, and our approach minimized the hazards because our main concern was to cut the pathways via which the hazards are transmitted, and of course allow some recreational purposes probably in the future. But another main point, another main let's say, detail that we also exploit here in the Mine.io project is that we have possibly a future ore. We have a future mine. So we may consider, this polluted, this hazardous waste landfill as a future mine. As my colleague Mario said before, several waste now with the new recovery techniques may be the ore of the future. For example, the quantity of copper that is located in all kinds of waste repositories around the world is almost 30% of the remaining reserves. You can imagine that this is a huge amount that we may recover from the waste of course, if it's techno-economically viable, without hurting any natural resources of copper. So, our approach with the waste repository, first of all, we minimize the risk for human health and the ecosystem, and the second is that we may consider this as a future mine. Of course, there are some disadvantages that we have to deal with, and the Mine.io project will assess those risks better than before. First of all, we have the pollutants that remain there. We have no reductions in their concentration. Isolated, yes, but they are there. And one of the other main disadvantages is that if something goes wrong, it's very difficult, expensive, and not environmental friendly to interfere. For example, if we have some maintenance or a repair needs within the layer, it's technically, in the view of engineering approach, is very difficult and dangerous to interfere. And of course, we have limitations, as you can imagine, for the use of the land above or in the surroundings of the landfill site. So, let's see some numbers and how we can expand these numbers to the future risk assessment approaches. First of all, we have 4 steps in the risk assessment process, 4 distinguished steps. Almost all the experts in this field agree that this is the fundamentals of the risk assessment. Hazard identification, dose response assessment, exposure assessment, and then risk characterization. Our main target, is to quantify the risk, to have a number, not only for us, but also for public authorities and the public in general. It's much better to say that the possibility that something will happen to you is 1 in a million, rather than to say that arsenic concentration is 2,000 ppm. Nobody understands. But with numbers, possibilities, it's much more easier to get things going. So our main target here is to characterize the risk and give a specific number. Here is also a view that is probably more or less understandable to the public. What are the main pathways starting from the source of the pollution and the final target, that is humans or the ecosystem, and how we may cut off this chain. So, risk-based approaches, this is the key here. We perform a risk assessment and then we make our decision based on these numbers. More or less, this is the only techno-economically viable way to deal, especially when it comes to waste like mining and metallurgical waste. So this is a very quick view on maths. Of course, there are several models that they can explain and calculate the risk depending on specific parameters that we give. Here you can see one of those models broadly used by the US Environmental Protection Agency. It concerns specific effect, carcinogenic, specific waste route, ingestion, and a specific part of the population, a worker. All this can be differentiated and give us different equations with different parameters. But this is not the scope of this workshop. Here we'll give some brief example of how we calculate the risk. So you can see that the acceptable risk here, it's 1 in a million for the carcinogenic effects. And we use here, the advantage of this method is that we may use immediately the concentrations of the surface element, for example, for arsenic. So with the same philosophy, we deal with non-carcinogenic effects. Okay, here we use the hazardous quotient. The acceptable number is 1. It's a slightly different equation, always depending on the element that we choose. And also, we are referring to specific exposure route, to specific effects and specific targeted population. Here are some parameters for some key elements that included in the equations. All these parameters may refer to ingestion, inhalation, and dermal contact of those elements. For some of them, you can see that there are no data, okay, because it's very difficult to translate epidemiological data to numbers, okay. Even with the technology, progress these days, it's very difficult to perform epidemiological studies because they are taking so many years. But we have a decent, let's say, database to transform some basic data for conducting risk assessment calculations. So, let's see some numbers now. The risk without the repository. As you can see, for example, the carcinogenic risk for ingestion was 1,500 times greater than the acceptable limit. Okay, this is very interesting. I'm talking without our approach with the repository, not now. Okay. Another important pathway, another important result of these risk assessment considerations is that most of you will expect that inhalation was the most probable, the most hazardous route. Now, it's not the case. As you can see, the inhalation risk is almost 1,000 times less than the one coming from ingestion. So the main risk in our case, and in most mining and metallurgical sites, is coming from ingestion. The only exception is when we are dealing with chromium, but this is another discussion. So, main risks and questions involved now, and how we are going to use the technologies that we have in our possession in order to take risk assessment one step further. First of all, we need to study the stability of the embankment. What is the status of the isolation measures? If we have water intrusion on the waste mass, if we have any indications of hazardous metals and metalloids that are escaping from our embankment, the surface status, okay, the groundwater status that we're continuously monitoring, the distribution of metals, especially if we may consider this as a future mine. And of course, for the same reason, to balance the risk and the benefits if we choose to exploit the waste as an ore. Here is some indicative results from the last 12 months from boreholes around the area. You can see that we have some exceedances of the acceptable limits. This is not risk-based values. There are values coming from a regulatory framework. Okay. You can see that there are, especially for arsenic, values are very, very low. I mean, you can see that the maximum value here is 45 micrograms per liter. For some equipment, this is even difficult to measure. Okay, there are very, very strict limits. Okay, so it's not for someone to be scared, okay, by looking at these results, because even if we have exceedances of the limits, okay, the concentrations are remaining very, very low. But if we translated this to risk assessment, we may calculate the risk if someone ingests this water, which is more than unlikely, but just to have a look of how we may translate these monitoring results to real numbers. Okay. The risk, for example, for carcinogenic effects for ingestion of groundwater exceeds the limit. Okay, here it's almost 10 times greater, 7.93 10 in minus 5. Okay, and of course, calculations are based on average concentrations. Okay, and we may calculate different results if we consider inhabitants, if we consider different pathways, etc., etc. But to have a first view of what we are dealing with, this is the base of the risk assessment. Okay, so let's see now how we use modern technology in order to go these risk assessment approaches further. Okay, first of all, with our colleagues in MineIO project, and especially the University of Salamanca and the Axeliges Ltd. That have provided the drones, okay, we performed a series of different technological approaches based on sensor, not invasive techniques, okay, to assess the pilot site in Lavrion, the repository. First of all, proactive risk assessment. Here we use DINSAR, okay, and we focus on the stability of the embankment. We can see how vertical and horizontal velocities of the embankment are changing during time. Okay, and we can have the first prediction of what is happening with the stability of the embankment. Our general approach up to now, after the first set of measurements, is that stability is in a very good situation. Remember that this is a structure that was made 16 years ago. It's not something new. Okay, so these results are relatively good for us. Okay. Drone magnetometer. Okay, we are flying the drone with the magnetometer, and we may take results remotely, referring the status of the embankment. We also have a series of measurements next week, also the second drone flight in 1 year in Lavrion the next week. And here you can see some results from the drone magnetometer. We are focusing on understanding the spatial distribution and concentration of waste based on this technique. You can see the different colors, especially in the left picture, where the zone with high values are probably related to areas with higher concentration of ferromagnetic material, such as iron and nickel probably, but usually we don't have nickel in Lavrion. Okay, so probably this is iron. And the other areas are covered by non-ferromagnetic materials. And we have also developed a very interesting 3D model of the site, where we can see in the 3 dimensions where the waste have been posited. This is very important, okay, not only for purposes of environmental management, but also for the approach that we have described before to see this embankment as a future mine. You can see that lead arsenic and cadmium, this is the very interesting thing, that are the most hazardous elements in our case, are the ones with very low ferromagnetic attributes. So it's much more easier for us to detect them within the waste mass. And finally, ground-penetrating radar. You can see how the field work is done and how we are taking software insights for our repository. This is some preliminary results that are very interesting. First of all, we can measure, we may detect the possible pollution pathways, okay, especially from the surface top coverage. And we have detected, indeed, places in the waste mass where water intrusion is happening. We are not sure and we don't believe that has passed through the rest of the layers, but probably we have an intrusion in specific places within the first geotextile layer. So this is our first step in the future to try and solve this problem. First of all, scan the whole area and detect all the places that may be a possible pollution pathway, and then take remediation measures. So, some main conclusions about our approach with respect to the risk assessment using new technologies. First of all, the DIN-SAR provides real-time and precise monitoring ground deformation, especially for the stability of the embankment. The drone magnetometer gives us non-invasive data that make us understand the spatial distribution of the waste within the repository mass, especially in case that we have to consider this as a resource in the future. And of course, ground-penetrating radar reveals hidden structures and detecting potential contamination pathways, always refer to the landfill stability, and guide us for the immediate remediation measures that have to be taken in the near future. So our future work includes the monitoring of the humidity of the mining deposit, the correlation of these humidity measurements with ground-penetrating radar results, which is very important, to see the status of the deeper insulation layers, which is not revealed yet, okay, which is a very important parameter, and to integrate all the technologies and propose specific remediation techniques and specific routes that we may consider for the recovery of materials. And of course, try to quantify the risk, to have numbers again about estimating the rate of deformation, define the degree of the slope movement, performing risk zoning, identifying what are the risk zones, especially for leachate production, and quantify this leachate portion, locating leachate pathways, and of course, make the most accurate and detailed assessment of the cap and liner condition, especially in the sides and in the bottom, where it's much more difficult to get. So that's all for me. Thank you very much for your attention. I'm open to any questions.
Am I online? Not yet. Just a few seconds more. Yeah, I'm online. Thank you, Vasileios, for the presentation. Great job.
Thank you very much.
Now we can move on to the Mentimeter questions. You can see some slides with the Mentimeter questions just in a few seconds. Here you can also see the code if you missed that. So in just a few seconds, we will crop up the first questions. Not yet. We will just be ready shortly. Yeah, here it is. So The first question is, do you know how many years monitoring of a mine deposit with environmental sensitive materials should continue post-mine abandonment? So this is the legislative question. Let's see about the answers.
I will be surprised if any other answer will be given.
Don't give a hint. Although we are not at an exam period.
It means that we have lawyers among us.
They are basically well-informed people. Okay, it seems that you give a good hint on what...
Just a small comment here.
Sure.
Of course, it's more than obvious that you have, especially when we are dealing with metals that have a very long life, and they are not decomposed like usual wastes, okay. The point is that even in this case, okay, you have to monitor almost forever, okay. Because in Lavrion, for example, we find places with ancient waste that are almost intact. Slugs coming from the Asian and Athenians that are almost intact. Because all the metals inside have a very large life potential. Yeah. So the same thing happens here, and I'm very glad that I can see that all the answers are correct. Okay.
Yeah. I think we will touch on the...
It's very different to monitor a landfill, typical landfill site containing typical household wastes, and a very different thing. For example, here we have also, in metal, let's say, repositories, we have the disadvantage, let's say, that we have to monitor almost forever, but we have no gas. So people have to distinguish this in their minds. There are pros and cons in every case.
That's true. And on the topic that you already touched on, so tailings, we will have the next presentation.
Yes, yes.
So
Raul is much more experienced than me in this
on environmental
field.
issues, but good point of pointing out. Maybe let's us move to the next question. Mm-hmm. Okay. The question that we have here, do you think that the environmental remediation of an old mine deposit is compatible with the economic exploitation of this process? So, waiting for your answer. So again, don't be shy.
It's a very tricky question. I mean...
That's why they are hesitating. Okay. Now I read you. Okay, now we are missing only answer no to have them all marked. Any more feedback from you? Okay, we have two answers that are, let's say, striking out. The first one is yes, and the second one, it depends. So, if it depends,
it goes
what
to the yes, you know,
goes to the yes.
To the yes.
If it depends, it depends on what, or if it's yes, then can you elaborate on that?
It's a very complicated answer in this case because there are a huge number of parameters and factors that we have to take on mind in order to develop any solution and to prove that this is economically viable. Okay, especially when it refers to the old mine. But first of all, the environmental restoration of an old mine is more or less a duty. So no matter what, if you want to be, let's say, to do your duty as a public authority or for the people that are surrounding the mine, okay, the restoration is imminent, okay, because their safety is first. The second part goes to probably the answer C, okay. If we choose to do something like this, what are the parameters that we have to bear in mind? Okay, and of course, the land uses, very important. I start from there. Can we have, after environmental restoration, a new land use that may be like in Lavrion, because we have a cultural park and we have revenues, okay, for example. Second, is there anything left to exploit? Raul will also give an insight in this in the next presentation. And generally, when it comes to techno-economical answers and issues, things are getting many parameters that it's very difficult to answer if you are not targeted in a specific case, like Lavrion or like Oulu and your site in Poland and all this.
Okay, I'm very happy.
So it's true that the 11 is true, okay. But here we have to discuss for hours if we want to be more specific.
Yeah, I'm very happy that you touched on the combination of social and economical aspects, which basically bond into responsibility of the people and basically environment.
And the good thing is that also the regulatory framework gives more and more ground to the social assessment, to the social impact assessment, except from the traditional environmental approach.
Okay, great. We have one more question here. Then maybe we can move on to the last question that we have here. Do you know of any remote sensing-based technique for non-in situ monitoring of sensitive mining deposits? So this is that you can insert your responses.
Probably the point is that if they knew something before or what they know now, because we have described, okay, I have to be, to help them a little bit. We have described not invasive techniques.
Okay, you still would like to give them a hint that Myon is here. Yeah, so insert Myon here and we will be happy then, more than happy here, but because you can still find your own ideas to insert.
Because if you are not an expert, let's say even myself, before, okay, it's very difficult to know. Because it's a very high-tech field, okay? So it's very difficult to know.
Still, you have to be open-minded and you have to have a narrow knowledge. Okay, we got some answers filling in. So we got satellite information and Earth observation. So those are quite well combined.
Yeah, for example, the DIN-SAR technique mostly depends on satellite info. So this is correct. Okay, although it's much more complicated than to take a satellite picture. Okay, but the main principle, okay, is taking satellite pictures, let's say, in different time and compare them.
Okay. Yeah. So all this, what you described in the meantime of multispectral information, having them on a drone or any other equipment that basically flies around us. It can be, of course, satellite, it can be drone, depending on what kind of technique do you have. Any more answers that's supposed to fly in here? Or are we expecting something more from the attendees? If you have some answers, let us know. Maybe also a comment from you that you might think of additional techniques that can be helpful here?
Anything that can fly with a drone, like the magnetometer, okay. can give us valuable information for the site. If we don't want to be there, because the question said non-in situ monitoring. So if, let's say, we consider that ground penetrating radar, needs someone, to scan the area in situ, so we are talking about non-invasive techniques, not in situ techniques coming from satellites and Earth observation, it's very correct, and also with drones. So the magnetometer that we use, just hang in a drone, it's such a technique. Not in situ, because nothing touches the ground.
Yeah. Okay. Do we have any question that
Yes,
came?
we have some questions, but I will just take one. So.
Okay.
The question was, since you have a so high concentration of minerals in your waste, have you considered to sell it, so to say?
Sorry, what?
To sell the waste?
To sell it?
Yeah, to a mineral plant.
As a matter of fact, this is public information, so anyone that wants to buy it, we are open to discussion.
Negotiations.
Because, of course, there are those information, and that was the principle of the Lavron Technology Park from the beginning, to be clear about the situation within the borders of the park and in the whole Lavroitiki. So we are in very close cooperation with the local community. But the point is that this type of waste, it's a very good question, could be a future ore. We also have another pilot site, if you remember, that we are dealing with much more difficult and much more hazardous waste, if you remember, where it's a pilot site, the number 2 in Greece. There maybe it's much more possible to have a buyer in the future, because we have more concentrated waste. Here we have a mixture with soil. Although we have, let's say, 40% or 45% iron, this is something that we should consider. But we need, and I believe MineIO will help us to this, to make specific, to target the specific parameters of the waste, so as to have the whole package of information that a buyer will need.
Yeah, this is what struck me and stunned me in your presentation, that already in the waste deposits we are gathering 30% of minerals that can be digged out from.
Yes,
from
yes, especially for copper, this is true. That's the statistics. They are real numbers, yes.
Yeah, that's quite a lot. Of course, with the development of technologies that are around, and also we are working in MineIO, we can make it happen that less of the earth will be digged out, and we will take care of the deposits that we have here. Maybe we have one more questions. Okay, we ask one of the participants to mute their microphone. Okay, that's the sweet proposal to the people that are online to mute themselves. I think then we might move on. Vasileios, thank you again for this presentation. Insightful.
Thank you for the opportunity.
Next with us is Raul, that will lead the way towards again, we'll touch on the topic of environmental assessment and risk, together with tailings and all the things that are connected with it. Raul, the floor is yours.
Thank you, Marek. Yep. Hello, everyone. I'm representing here a team of colleagues that are behind this work, Oulu Mining School, University of Oulu Kerttu Institute, and of course the mining company supporting our pilot, Puhasalmi mine in Finland. So we will be talking about reliable surveillance operations that are connected to what we're doing with monitoring tailings facilities. Our approach here is basically look more into the physical aspects of the stability of tailings. And just to give a context of what are we tackling here. So this is a schematics that shows on the left side just a rough imagery of a mining operation extracting ore. And during the extraction, there is a separation of valuable ore that goes for processing and also rejects that are the waste rock dumps. So at first, we have still big piles of dumps of non-valuable resource that is going as a reject. But then after the process plant, there will be some separation, and only probably more than 95% and even more goes as a reject, as a waste. And that's the waste we're tackling here. That's the tailings. The tailings goes to storage facilities, purposely built with embankments. That's kind of the walls that will contain that waste. And to give an idea what type of material we're dealing here is kind of sand or sandy silt texture. During operation, this is how it looks like at tailings. There's all sort of challenges in managing tailings. There is a lot of water buildup. Managing water is one of the aspects. Managing the level of water is another one. But all that interaction with that wall that has been built to contain the tailings makes that embankment at the risks. We could have this infiltration of water into that embankment, and based on that, we can create these internal erosions that can damage the stability or the structural stability of these embankments. And when that happens, the embankment fails. And this is just a picture. I'm not going to talk about these issues or on failures, but just to picture a dimension of what happens when one of these dams collapse. There is environmental and social damage, but also there is financial loss. And these are just a couple of examples that happened recently, 2015, 2019. We're talking loss of lives, loss of villages, but also in terms of financial damage to companies. We're talking here billions of dollars of settlement. And companies, of course, they have to take this seriously. They need to monitor these tailings embankments, and that monitoring now is more stringent. So everybody is aware that we have to do this. There's a reason to do that, environmental, social, and also financially. Now, after those collapses in 2019, several important bodies in the mining industry, they agreed to take this on a platform that created a path to this global industry standard in tailings management. And that industry standard is setting the roadmap where we're going in terms of innovation and technology for monitoring tailings facilities. And there is a lot of studies behind this global standard. And the thing here is that the global standard is pushing mining companies and technology developers in creating new ways how to monitor tailings facilities. And if we see on the left side down below in this slide, those are pretty much the conventional technology that we've been using so far. And the global standard is pushing us to think more into the innovation aspects. And they have listed explicitly this sort of emerging technologies that we can use for monitoring tailings facilities, from earth observation, remote sensing, and also in situ measurements with non-invasive technologies. Because if we think more into detail how we manage tailings, we have to think that those are structurally something that we shouldn't disturb. And we have to think ways to measure what's happening beneath, but without doing too much test pitting or drill holes or sort of invasive measurements. Geophysics is one of the areas, and that's the area in which we are focusing at Oulu Mining School. What's the approach here? The question here is, can we use geophysics to get information from those embankments? We have explored all sorts of geophysical methods, and we came up with 2 of them that can potentially be used for the purpose that we want. This is something that many other researchers around the world, they have been using to get information on the geometry of tailings facilities. And if we see the upper, in the slide, the upper part is showing electrical resistivity imaging. And electrical resistivity imaging can pinpoint those areas in which that electrical resistivity distribution can be high or low. The contrast in that's based on the travel of the water in tailings of high electrical conductivity that can give us indication what are the flow paths of pore water. And so far, that has been the approach. The other method is seismic imaging. And seismic imaging, shallow imaging, we could use seismic refraction, or we could use with both active and passive source. And also targets the geometry of tailings based on density contrast and the distribution of these seismic velocities. Our approach here is to go one step further. So how can we translate that geophysical signature, electrical resistivity, and seismic velocities in something that operators can use, especially for planning or for monitoring? If we think about the structural stability of tailings, we have to think about geotechnical engineering. And geotechnical engineering normally goes into that sort of parameters that are linked to the elastic properties, which gives indication of the stiffness of the material. And that's what we want to do, transform seismic velocities into elastic properties, and therefore make some interpretation about the structural condition of the subsurface in those embankments. Likewise, with electrical resistivity imaging, we have electrical resistivity, but we want to link that to properties in that embankment that can be useful for the operators, like porosity, or like the phreatic line, or water saturation. So these sort of parameters is what we want to provide as an output after running these pilots in the MineIO project. So with that in mind, now we have to think, how do we do that? And how do we, I know most of the sensors that we have now in geophysics, they are digitized. So the data comes as in a digital form, but we have to transform into this path of the digital transition, something that we could use for productivity and to help the mining companies to use it. We find challenges in that. We know that the data is coming in different formats, binary data, and some of them they are tabular data, some of them they come as rasters, so images, and we're working on that in a way that we can make workflows that can produce us data that can be interpretable. So this is the approach. We have the embankment, and we are deploying electrical resistivity imaging with several electrodes. For this, we have had interactions with the mining company, and we asked them where in the tailings facilities we can deploy these sensors. And we have selected specific areas which are for interest for the mining operator. And the embankment is some sections of the embankment that I will show later has been chosen. So sensors, in terms of electrical resistivity, those are electrodes in an array that are separated a certain distance. And the principle here is that we are going to inject current in a couple of electrodes and measure the potential difference in another two, and then sequentially do several times that in an automated system that we are showing here on the right side. So we have electrical resistivity imaging system that has been assembled in a way that can connect to the web server. So the data that we are reading can be sent in almost real time to a server. And from the server, we can automate our workflows for pre-processing, processing, and visualization. So that's the work forward. With the seismic, also the work has been done in that area. We have selected specific types of geophones that work with SIM cards, 3G SIM cards, that are sending individually. That's the yellow logger that's showing down below, close to the right side in the slide. That logger, it's being connected to GPS. Gets the signal from the satellite for the GPS positioning, but at the same time, it has a SIM card that's connected to the mobile network that is sending the data in real time to a web server. So both systems are independent. They work in web servers that are separately. Now that the task here is to connect and bring all the data into a local server that we have at the university. And from there, the next step is to connect to the Mine.io platform, in which interested stakeholders can connect and access the data. So that's the project that's our task in Mine.io project. So we have started. I guess I mixed the slides. I was meant to show the pilot trial one, so I will look for that. So we started with this pilot trial one, and we deployed in that on the left side upper section figure. You see that area of the embankment that we have selected. So the Pujasalmi mine, they have this tailing storage facility that has been divided in cells. Each of them, they have a specific purpose. And the one that you see with the vegetation coverage, that's the old tailings facility that has been reclaimed. It doesn't look like that nowadays because that now has been repurposed for a solar farm. But we've been doing studies in that area. But the mining company, they asked us to do this research and development in the active tailings facility. So that part on the left side figure, we have this yellow dotted square. That's the area where we are deploying these sensors. Upper side on the right side, we have these 144 electrodes. That's for the electrical resistivity imaging. You have electrodes spacing every 5 meters put there in 4 lines. So with that, we meant to get signature and then get tomographic volumetric imaging of that section. Down below, we have an array of geophones that we have deployed. The first one, 480 geophones, those are specific geophones that are not with the capabilities to send data in real time. But the ones on the left side, the GSX, those are the experimental ones that we're testing that can send the data in real time to a web server. So from this experiment, we got preliminary results. And we have this imaging of the electrical resistivity imaging. The data that we are getting are those that we expect. And there is a range of values in between 1 ohms per meter to about 80 or 90, depending on the conditions of the embankment. We have to think that this is an embankment that contains not the tailings itself. It's a material, a geotechnical material that is less acid producing. So we expect that the resistivity in this should be higher, or yeah. So we can see that on the right side, that's the imaging that we have obtained. We have more updated imaging, and this is just an example of one day imaging, and we can have this sort of imaging for every day. So that's what we are aiming, a temporal resolution of imaging coming every day. So the mining can see that there is, if there is any change, can see on a daily basis. So you can see some of the areas are coherent with what we are seeing. On the right side of that volumetric imaging, we see more darker colors of low resistivity. That means that there is a pathway of water coming on that area. And in fact, there is, because there is a pump station down below that slope that is collecting that water. So that's very coherent with our findings. And this is the results from the seismic imaging. With the seismic imaging, and I have to mention that this is an approach with passive seismics. So even though the mining have ceased operations, so it's going under closure, there is not much activity there, and we have to resort the energy source from other means. And in this case, we're using regional seismic events from a catalog of these seismic events, and we're using those events to cut our signals that we have recorded with the loggers, and use that energy to start preparing the processing of the data. So the idea here is to process the seismic waves, looking the surface waves, and based on that, you see the lower figure on the left side. That's the dispersion curve of surface waves. So the phase velocity of those surface waves are inverted in a way we can get to the right side, which is the shear wave velocities. And shear wave velocities are the ones that we're interested in, because those are the ones connected to the elastic properties of the material in the embankment. So that's the results that we're having from the pilot trial one that ran May this year, in May 2024. And we have to think that the Arctic conditions, it's seasonal. Spring, May, is kind of dry environment, easy to deploy sensors, easy to go and work there. And now we have to test this in the winter conditions. So we have just deployed again the sensors a couple of weeks ago. And we will test the sensors until April next year. So we're testing the robustness of this deployment in those conditions where we will have snow coverage and harsh conditions in the slope and everything. This is the next pilot, and the array of the deployments we can see now on the right side pictures. Again, we're replicating the electrical resistivity deployment with the arrays, and then we have changed the approach in the seismic arise on that part on the right side, in the middle, down below, with 150 geophones. But this time, we want to target the whole tailings, not just one section of the embankment. We want to target the whole section of that tailings to make a tomographic imaging of that area. And again, we are replicating the other real-time sensors on the right side here with the GSXs. The rationale for that change in the array of the geophones in the perimeter of the tailings comes from the previous results that we had in previous measurements in the other tailings in that reclaimed part of the tailings, in which we have tested that putting in this type of arrays, we can use all these signals and select the rays of the geophones in a way that we can derive a tomographic image of surface waves. And if we have the surface wave, likewise, we can invert those surface waves back into shear waves on the right side down below, selecting any part on the tailings facility, like profiles, and then make these 2D sections of shear waves. So it's a more comprehensive approach of getting information from the subsurface of the whole entire facilities. So that's the rationale for the change on the arrays now in the active tailings. Well, so far the project, I think we're on track, and the work coming is that part of the integration. We are getting data, and we have to work now in that part of what really the MineIO is meant for, the digitalization of our workflows. And in that sense, we have to automate our workflows, kind of cloud computing. And we have to connect to the MineIO platform, so everybody, stakeholders, can get access for visualization on almost real time to what we're doing. And hopefully we will achieve that in the coming few months. So I want just to complete this presentation emphasizing on what really means this digitalization for us. Mining industry is kind of a table with 4 legs, and those are the key stakeholders, the 3 of them: the mining company, governments, and communities. And I think Vasileios has clearly pinpointed in this that there is a reason why we have to take a lot of emphasis on managing waste in mining. But not just, our point of view is the structural stability of tailings, but nowadays we're shifting a little bit more into looking at these facilities as secondary resource of minerals. And in that sense, there is a lot of room for making research and development on that aspect too. If we just think about the needs, everybody has a need. Every one of these 3 stakeholders has a need. But also I have included one additional column that is relevant for us, for the scientific community, in which there is room to go for innovation. And in what we're doing with our project, we are tackling these non-invasive methods for system characterization of tailings facilities. And transparency is one of the aspects that is needed, not just by the mining company, but also by the governments, regulators, by the community. So all is tied together to that confidence in the industry, and also gaining the trust. We need more mining projects, but responsible and sustainable. And I think this is a way in which we can contribute to give more support that there exists innovation, high technology, and reliability on monitoring systems that can cover more holistically. Practice nowadays is more focused on discrete points of measurements, We're still in some operations. We're still doing this visually. But yeah, I'm glad everything is progressing into this digital transition in mining. With that, thank you for the opportunity. And yep, questions now or after to that email. Thank you. Thank you, Mark.
Okay. Thank you, Raul, for your talk. Just right away, I have a remark to one of your last slides.
Yep.
Thank you for showing that the aspect basically touches all the area that are not only industry, it also touches the community which is around, and researchers like one of us that
Yes.
can help in reaching the goals.
Yes.
I will ask one question from my own before we go to the Mentimeter.
Yes, of course.
How about data fusion and any chances of collecting this data from geophones and resistance method? And also one following up questions that
Yeah.
I will ask is about the active method of the seismic. You said it's coming, or it will be planned in the future?
The first one first, the data fusion. That's one of our objectives in this project. I haven't mentioned, but I should have. We are getting at first stage those models based on our geophysical signature, electrical resistivity, and the seismic velocities. The data fusion, to get that information in terms of elastic properties or hydrogeological conditions, we need to fuse the data. So we will fuse the seismic outputs with the electrical resistivity outputs, in addition to the information that we get from the tailings embankment. Because we don't need to guess in tailings embankment. Those have been built by its man-made structure. We know the geometry, and we could use that information to constrain our modeling. So we're getting more precise in that.
Yeah, thank you.
And the last question was about the active source.
Yeah.
Where our research started with active source seismics, but we are moving more into the passive source seismic because it doesn't need. It's kind of more independent. Doesn't rely in somebody hitting somewhere or making some small explosions, anything. Okay. It's just getting ambient noise or seismic events. So it's kind of passive and much better. And I think the industry is moving into that passive monitoring. That's, I think, the way forward.
Okay, thank you for explanation. I didn't know that. Let us move to the Mentimeter questions. So we got 3 of them waiting for us. If we share the screen, here you got the first one. What is in the order of importance, improving environmental monitoring in mining via reliable systems? Rank them, and the one is the most significant. Sorry for that.
Yeah, I could add. Not for me. Yes, not for me. Yeah.
You have to wait for the answers.
Yeah.
Just a few seconds. Or you want to comment?
Just provide a comment on this. It's not right or wrong answer here. It's just to collect the perception of the audience in terms of how they think. It's just ranking. So all of them are correct. It's just the perception. What's more important for them?
Okay, we got first answer here, but we are waiting for them to align. We will see if they align the same and if we get more answers. Mm-hmm. That's good. The informations are flowing in. That's nice. Mm. Okay, as Raul said, there are no wrong answers. We would like to only hear your perception and see how you basically judge those in the ranking from the most significant to the least significant. But first thought on what's mentioned here as one of the first ones?
Yeah, it really, it's coherent with what we have everywhere in research or in the industry. That perception, because most of the things that mining companies they do is protect public health and safety. That's important. Yep. But also environmental values, environmental and social values, and that comes in second there, which is good. But this might shift depending on the audience. But I guess this is a more generalized audience that is tuned with what we can read anywhere. Yeah.
Okay. Shall we move then to the next question?
Yes.
Then let's move to the next question that is here. Again, a ranking. Rank the following options in terms of how much advantage they can receive from digitalized monitoring and surveillance systems. So you got 5 of them, so not too many, but some relevant for us to see. What's your perspective again?
Yeah. Well, there are 2 types of transition happening now in the industry. One is the digital transition. The second, the energy transition. But in terms of the digital transition, how do we use the digital tools and for what? And that's a question, I guess, for the users, operators, and everyone involved on mining. And we've seen in the first Mentimeter question that goes into public safety and environmental values and social values. But I guess here also we will see some similar pattern. Yeah. Yeah, we see the environmental risk management there.
And one of our first slides that we showed here about Mine.io was basically Mine.io is about digitalization. So we would like to fuse the data as much as possible, build on a platform from that. So here you go. Okay, we see some changes, but we don't have a real leader here. It's head-to-head. Seems to be, and also the points that the last presentation basically touched on. So environmental risk management is here. So Vasileios and Raul had made a good job with educating you guys here and making you sensitive about the content that was presented here. Let's go to the last question here that we do have.
Maybe I can comment.
Sure.
I'm really surprised the one coming last, community engagement and development, and that's one of the things that we want to improve with the digitalization.
Yeah.
Because at the moment that's one of the challenges in gaining the trust of community into the industry, and that sort of engagement now with the digitalization can ramp up that.
Maybe I will refer to Vasileios' presentation that basically it's hard to convey the message when you're talking about the numbers. It's very hard to talk to people that are not technically minded and basically to what the message you are trying to convey.
Yeah. And I guess that's one task for us in terms of conveying that message. The visualization of this platform will convey that. Probably imagery is a good way to convey that information,
Okay. Maybe we'll go to the last slide that we have here with the questions. And here you got, in your opinion, which emerging technologies will drive development and industry adoption in the near future? So here you got few technologies mentioned and also mentioned during your presentation here and also in the last previous one from Vasileios about different techniques. So you can choose and rank and we will see and discuss that. So go ahead, viewers and attendees. Okay, we can see that the drone techniques are striking out as the leader of this heat, let's call it. So, but we got few other options here coming. So, a brief comment from you, Raul, about the results that we see here
Yeah, that's
as they're coming in.
yeah. From my point of view, that's it's good, well reflected, I think. But we have to think that we need a lot of cooperation here with drone-based monitoring, because what we're monitoring with drones is the surface.
Yeah, that's true.
And we also have to monitor what's beneath the ground. And that's those two there with geophysics. And in order to have this holistic monitoring, surface and subsurface, I think those three are well put there. And I'm not saying that the others, those are the ones that the global industry standard have listed as something that we have to look at.
Yeah.
But all of them, they have their own merits. Satellite imagery is good for planning, although it lacks the resolution that we can get with drones and with local geophysics. But I think we should try to use all of them and then make this data fusion that you mentioned come together. Yeah.
Also with the satellite, the world is changing and basically higher resolutions can be achievable. The only problem is the up and downlink of the information, that basically the enormous amount of data that you can grab from a satellite, and more of them are happening around us.
Yeah.
So it's enormous. So we got some answers here, also trying to be covering the topics that we mentioned, so we are happy that we managed to cover them up during this workshop. Are there any questions, immediate questions that we have from attendees?
Yeah, I have a question. You have touched it already, so but it's you are using passive sensors for this, and you have so to say the mine is not active. In an active mine, will that be a better way of using the passive?
Yes.
Is it a?
There is more, let's say, energy coming from an active mine that we could use.
Yeah, from the blasting and.
Yeah, from the blasting. Yeah, especially that one.
Yeah.
Yeah, from the blasting and the operations that happens on the ground and everything. But when the mine ceases, there is nothing there. It's just probably some traffics. But sometimes those can be disturbing in terms of frequency. But it's better to have these high amplitude sources. And we're trying to use those seismic events now, because that happens everywhere and every day. 20, 30 of those events happening in Finland here. So we're filtering those seismic events and using as energy sources.
Then a follow-up question to the answer or asked by Jan. Would that help in a sense that you mentioned that the sensors are, let's say, stuck there, but you cannot retrieve the data? So would that be helpful to digitalize and basically send over the data?
Yes.
Right away.
So we have two types of sensors now in the pilot. Ones that they cannot send the data, but ones that they can send. And we're using both of them because of one of the challenges that you mentioned about the size of the data. So every one of those loggers can record about, can't remember, it's about half terabyte in a month. So sending this in real time, it could saturate any network. So we have to be very selective in what we send. Yeah. And those that they don't send the data instantly, we're using that to test our approach, our processing. And those that can send data in real time, we're testing that to filter in the data and send just a specific bits of information. Yeah.
Yeah, so basically some AI additional features to analyze the data and let's say, remove the crappy information that are, let's say, not
Yeah.
relevant, but basically the algorithm's supposed to be learned and taught how to send relevant information
Yeah, correct.
right away.
Yeah.
Okay, perfect. Any additional questions? Or?
We can take them later.
Okay, then we can take them later. So we will. There is one question. Sure.
Hi, Raul. I just want to know about the tailing embankments. Do you treat it as a homogeneous body, or do you have some, let's say, layers of different expected responses, different grain size? And if so, how do you treat the results you get from all these devices on the different layerings?
Yeah, that's a good question. They are not homogeneous material in the tailings embankment. On a micro scale, let's say the tailings itself that's behind the embankment, those we can see as homogeneous on a macro scale, because some people would say, no, they're not the same. But that's another part. The embankment itself is a man-made structure. So they have been built specifically for one purpose with different types of materials. They have different sort of materials that are not tailings. These are like something that can compact and be resistant. So they use clay. In the case of our pilot is steel. They compact, and they can compact in different layers. And just at the top, they have a little bit of coarse tailings that have been segregated and to use as a rising material of the embankment. So in a way, we know, we have information at what are the layers, at what depth, and we use that information to constrain our inversion models. So we will have to use. We don't need to guess on, our approach is not looking into the geometry or different densities because we already have that information of the construction drawings of those embankments. Now we are using that to derive our geophysical signature into these other type of parameters like elastic properties, or hydrogeological conditions, Does that answer your question? Yeah, cool.
Okay, thank you for the question. I think we can thank Raul for the presentation.
Thank you.
And we plan now to have a short break. We will reconvene at 1 o'clock. The people that are online, you have the possibility to watch 3 movies that we have prepared for you. And we got a colleague, the technical lead here also, Katarina, that will, if you have any questions directly after showing the movies, that you can ask her. And see you back in 1 o'clock.
Thank you.
Thank you.
Discover a holistic digital mine 4.0 ecosystem. Underwater robots to inspect flooded areas of the mine and hyperspectral imaging for the evaluation of the fragmented ore. Tomography technology used to obtain information not achievable by other means and to reduce invasive operations such as drilling. Real-time monitoring and optimization of the drilling process and environmental monitoring. Digitization drill operations, advanced digital mining maintenance, digital twin to monitor the mine. electrification of underground mobility, ore transportation monitoring and automation, classification of materials on stockpiles and waste by X-ray and drones equipped with magnetometry sensors, automation of processes for estimating ore reserves and deposits, ore flotations and smelting technology processes based on digital twin, big data and AI, control centers aimed at optimizing mining operations, maintenance activities, production and improving safety conditions, mining planning tool with end-to-end value chain visibility to manage energy supply, waste recycling and or exports, workflow automation and smart contracts, increased speed and security of data acquisition and processing, cybersecurity, blockchain, PLM. See the entire video about Industry 4.0 for the Mine.io value chain on our website. Read the report from our last workshop, register for the next one, and develop the Mine.io system with us. Find out more about Mine.io on our social media and website.
Mine.io aims to provide solutions that will build a novel mining digital ecosystem and a systemic structure for the implementation of Industry 4.0 in mining industrial environments. The architecture of the Mine.io system is based on 3 securely integrated layers. A pilot layer as a secure OT area for local digital solutions dedicated to exploration or extraction, mineral processing and waste management processes. Mine.io platform layer as a unified area of cloud-based digital tools such as pilot-driven repos, big data platform, cybersecurity tools and PLM module. Cloud services layer as an area dedicated to end users and business users. This layer enables the automation and optimization of plant-level processes in mining corporations. Let's look at OT layer solutions dedicated to exploration and/or extraction. Muon-based technology implemented for use by unmanned underwater vehicles, UAVs, to image and monitor the composition of underwater structures will facilitate underwater exploration of flooded mines. Meanwhile, the technology of analyzing materials and structures using X-ray techniques or the use of cyber-physical systems, CPS, to monitor and control drilling operations can be used during both exploration and/or extraction processes. The electrification of underground trucks as well as the corresponding digital organization and planning of tasks and responsibilities using AI techniques for predictive maintenance are other innovative solutions to support ore extraction. One session of today's workshop will focus on muon-based technology implemented for use by an underwater vehicle. During the workshop, you will also be able to see how we are using artificial intelligence and digital twin technology to digitize drilling operations, mine monitoring processes, and preventive maintenance. Presented solutions from the OT layer will be securely integrated into the cloud layer using a remote sensing and edge processing module.
Let's look at OT layer solutions dedicated to mineral processing and waste management. Ore from the extraction process is pre-crushed and fed to size control, to sieving for samples into primary and secondary materials or waste, making further logistics of pre-sorted ore more efficient. Unusable waste is removed early in the value chain, and the use of blockchain technology makes it easier to track and manage logistics. Mine.io is developing sensor-based systems for stockpile inventory, systems using artificial intelligence and machine learning to optimize the flotation process, and sensor-based systems to support tailings management. All of this, combined with digital twin technology in the ore smelting process, helps to optimize the removal of impurities and the recovery of valuable metals while reducing CO2 emissions, and enables more efficient processing of minerals and the creation of optimized stockpile-specific production campaigns. One session of today's workshop will focus on the problems of pre-classification of stockpile materials and waste management. We will show how using advanced methods such as drone magnetometry, advanced satellite methods, E.G, INSA, GPR, and hyperspectral cameras can accurately characterize a selected site. During the workshop, you will also be able to see how we are using multi-source geophysical data fusion for surveillance of tailings embankments. The OT layer solutions presented will be securely integrated into the cloud layer using a remote sensing and edge processing module, enabling managers to use a range of innovative services to optimize the production process. The Mine.io project also addresses the all-important socio-environmental aspects by implementing tools and related services to analyze these issues. Studies of social impact and benefits, as well as assessments of related indicators, will be carried out during the life cycle of the Mine.io system for selected communities of a particular area of the Mine.io value chain.
Welcome to Labrio. This is the first time that we are going to integrate different geotechnologies. In particular, we are going to use a LiDAR, a GeoSLAM that allows us to record everything in 3 dimensions and real time. We are also trying to survey some parts of the mining with UAV, integrating a magnetometer in order to see the mechanical and the minerals of the subsoil.
Mine.io will develop a highly innovative digital ecosystem that will facilitate the implementation of Industry 4.0 in mining industrial environments. The Mine.io ecosystem will be demonstrated in different sites involving operational mine sites and historical mine sites, such as the Lavrio historical mine site in Greece.
Last but not least, we are going to integrate the ground-penetrating radar, the hyperspectral sensor. These two sensors allow us to record the subsoil in the case of the ground-penetrating radar, and also to assess the different minerals, the different properties of the minerals with the hyperspectral camera. So we can apply different classification strategies based on artificial intelligence, computer vision. So the idea is to provide a geographical information system, a digital twin of the mining, combining all these technologies together, so the owners and the different end users in Mine.io project can assess the different waste, different minerals in a proper way.
Lavrio is situated in the southern part of the Attica Peninsula, 62 kilometers from the center of Athens. It has a unique historical background, since mining and geological operations started here almost 3,000 years BC. This area seems to be an ideal place for the development of the Mine.io concept, especially with respect to waste management.
I'm throwing stones against your window.
Okay,
More or less.
we can catch you now.
Shall we start? Yeah, we are on, probably. Welcome back. We got our last presentation ahead. So last but not least, this presentation will be presented by Dimitris and Max. So we will have both of them speak to you about the core of what's happening in MineIO about the platform.
Thank you. Thank you, Marek, for giving the floor to me. So what we're going to present now is the data management in future mines and how we're going to maximize the value from the data. I forgot to present, to introduce myself. I'm Dimitris Kassimis from Innovact, and this is my colleague Max Friedemann from TUBAF, and we're going to present the topic that I just mentioned before, and especially we're dealing with the MineIO cloud platform and the use case in the TUBAF pilot. What I would like to say is that from our side, we're responsible for, Innovact, we're responsible for the big data platform, for the development of the big data platform, which will be developed in the MineIO cloud platform. And of course, my presentation will be on how we're going to do that in terms of that we had to identify the challenges and we have to tackle from the MineIO cloud platform perspective. Then I will introduce you the high-level reference architecture, then the MineIO concept, how we conceptualize the MineIO, then the MineIO platform itself, and then the big data platform. Starting with the challenges that we had to tackle from the MineIO platform's perspective, trying to answer what and why we're developing the MineIO platform for the mining, for the future in mining. So we identified some, the first challenge that we identified was the digital maturity. We observed, the low digital adoption due to legacy systems and outdated technologies. As you know, in mining, there are some, let's say, devices that are outdated, and we have to digitize. Also, we observed the pilot's diverse needs. We have to cover different requirements across the pilot sites, and we had to integrate different technologies and processes which hinder the seamless integration. Furthermore, we observed the silhouette operations and the supply chain gaps. I don't know what happens, and the slides changes. We observed limited data exchange and sharing, causing delays and inefficiencies. And also, we're facing some, let's say, inefficiencies in the context of the information technology and the operation technology. So we had to deal with the convergence of IT and OT. And we had, in this respect, we had to enable a unified data-driven decision-making environment. Last but not least, we faced the future enhancements, and mostly we're focusing on remote monitoring and the connectivity for, let's say, innovative mining. As I said before, we designed and developed the Mine.io reference architecture. As you can see here, we have, let's say, divided the mining into pillars and into functional domains. On the left side, you can see the division that we have conceptualized, and we have the mining operation, and trying to include the Mine.io technology solutions there. In the middle pillar, we have the support activities, consisting of non-mining Mine.io technological solutions. And on the right side, we have the supply chain operations, consisting of the mining-relevant supplementary solutions. All these three pillars are connected and crossed, let's say, from the digital infrastructure. So this is the solutions that Mine.io provides for networking and communication. Here you can see the conceptual view of the Mine.io, trying to answer how we're going to tackle these challenges. As you can see, we have a schema trying to divide the digital world and the real world in mining. So in the real world, below, you can see the main mining operations, which is the exploration, the ore extraction, the mineral processing, and the waste management. This is mostly the mining operations, the core mining operations that Mine.io deals with. In the upper level, we have the digital world, consisting of, let's say, a pyramid, which is the Mine.io cloud. And the Mine.io cloud includes the digital platform and the digital solutions. This is how we firstly approached the Mine.io. Secondly, trying again to address how we're going to tackle these challenges, we designed the Mine.io platform architecture. And as you can see here, firstly, I would like to say that, of course, we're affected by the high-level reference architecture. It was the first schema that we presented. And we tried to have an abstraction layered approach. We divided our approach in two main pillars. The enterprise premises, which is below, and above the Mine.io cloud. Trying to converge the high-level architecture and the abstraction layers approach that we established, we came to the result in clustering the Mine.io solutions in mining operations and aligning with the support activities, the supply chain operations, and the digital infrastructure. This is our approach in order to be aligned with the high-level reference architecture of the first slide. Here, we would like to introduce the enterprise premises as abstracted layers. Here we have the field layer, the workset layer, and the pilot layer. The pilot layer, from how we would like to approach the Mine.io, we would like to include the sensors, the machinery, the trucks, whatever device is used in the field. Secondly, in the workset layer, we would like to include all the systems close to the field, including communication with the sensors, basic processing and control, and upper we have the pilot layer. It's mostly the remote sensing layer and the edge devices, which is responsible for the communication between the Mine.io cloud and the other layers of more close to the field. Here we have a schema regarding the Mine.io cloud platform, trying again to address the how on we're going to tackle the challenges. Here we have the Mine.io cloud services and the Mine.io platform. In the Mine.io cloud services, we have the supportive non-mining cloud-based solutions, including the predictive maintenance module, the social sustainability module, the workflow automation engine, the workflow scheduling and planning module, and maybe other cloud services that could be integrated with the Mine.io cloud platform. On the bottom side of the schema, we have the Mine.io platform, which mostly it's consisting of all the infrastructure elements and the cloud solutions, providing the necessary hardware and networking infrastructure to deploy and operate various functionalities and cloud-based services. So as you can see here, we have the data asset cataloging, the real-time streams, the individual pilot storages, and the PLM module. Here is a schema which tries to explain in a more detailed way the big data platform, and which is the core of the Mine.io platform. As you can see, the big data platform consists of the supported data repositories. This is mostly the pre-existing and the new storage solutions of the pilots. For instance, it could be the MongoDB or Hadoop or Elasticsearch and whatever could be an individual pilot storage solution. Then we have the data asset cataloging engine, which is responsible for indexing data, describing the type, the model, and the storage location. Then we have included the real-time data streaming. Mostly it will be enabled and supported by Kafka, which tries to handle real-time data streams. And then we have the REST API, trying to support data asset management, exchange and sharing, and enable CRUD operations. Lastly, we have the connectors, responsible for enabling interoperability with various storage solutions. Here we have the big data platform integration. From the northbound side, we have the communication layer with both MineIO gateways and cloud services via two different integration patterns. We have included the HTTP-based request response exposed through REST API, and we have a message-oriented for real-time streaming supported with Kafka. From the southbound side, we have the storage solutions, and that will be managed through connectors. So here you can see the use case view of the big data platform. It would be difficult, let's say, to be more to explain in a detailed way what is this flow or process diagram, but I would say that in this schema we're trying to present the data asset definition through CRUD connector, CRUD data asset, and search data asset. And the data storage or retrieval through storage data, get stored data, and the real-time streaming manipulation through stream data and consume data. So what is the big data platform's significance and impact? In this respect, we would like to provide distributed data storage, also supporting multiple pilot-driven data storage solutions. We would like to provide expandability and scalability. So this platform will be able to support a new pilot and only with a new connector, nothing more. So also we would like to provide fundability through the data asset cataloging engine, and of course accessibility through the open API. Also, if you remember from the latest schema, we have included the ISO PLM module, the ISO 10303, and through the PLM module, we would like to support interoperability between the systems. Also, the reusability of the data are crucial, and the versatility of course, of the data is crucial as well. With the big data platform, we will be able to support and handle a wide variety of data types, formats, and sources. Also, all this stuff will be crossed by security, and LTU supports this aspect by security by design. So this is the architecture which is applicable for the TOBAF pilot. And later on, I will pass the floor to Max. But of course, this is an introduction schema where we're trying, as you can see, with Kafka to, let's say, push the data from the pilot to the big data platform or to the MineIO cloud platform. So the Kafka will be responsible for that. We will push the data to the big data platform. So the big data platform will be the consumer of the data from the pilot. And then the big data platform will push the data to the cloud services. Also, in this pilot site, PLA module will be used as a storage solution. And what is significant there is to be able to provide real data streaming. This will be managed with Kafka, since the predictive maintenance algorithms need the real-time data streams in order to provide insights for the health of the drill rig of this pilot. So the predictive maintenance module will be the consumer of the data from the big data platform, and then will provide some insights, probably to the workflow automation engine. So simultaneously, it will be both consumer and producer. So I'll give the floor to my colleague Max in order to present the following of this presentation.
Thank you very much. Thank you very much, Dimitris. I will now present the other side of this platform. So Dimitris presented all the MineIO platform, all the way what's happening in the cloud. And now I will go to the left side, to the mine. And for this, I will start with the sensors, data acquisition system, and data management system. And I will explain how you get your normal how to get a normal drill rig into the digital mine 4.0 ecosystem. And for this, we have one big task at our platform. It's about the digitization of drill operations. And for this task, we equip our Sandvik DA110 with a data logging system. And with this data logging system, different sensors are installed at the drill rig, and all the measurement data will be transmitted via real-time into the MineIO platform, which explained Dimitris earlier. Afterwards, we operate this Sandvik DA110 in our mine, and we do test drillings at low-well locations, and also use different situations in the mine to get some data about it. For example, to use different drill bits. We have different objectives that will be inside of this task. So the first is we have a dashboard at the drill rig, and we want to provide the operator with detailed status about the current situation of the drilling. So we want to get there the current borehole length, it is really exact, and also get the speed of the drilling, and so some parameters to get an easier drilling process for the operator. And also with this example to increase the efficiency of the drilling process. And with all the data you know from the drilling rig, you will have a better learning curve for new operators. And after this, we have another 2 partners of the MineIO project. It's the LTU here from Luleå. And with this, we want to evaluate and analyze the rock being drilled in real time. And the second one is to analyze the wear of the drill bit also in real time. And now I want to be a little bit more detailed in these 2 parts. The first one is the material evaluation during drilling. And for this one, we're using tools for data filtering and normalization, which is the first phase of data processing. And the second one is to evaluate the drilling situation with AI-supported analyses. And for this, we want to identify the boundaries between the ore vein and the host rock, which is the most important for the operator, because normally you want to drill in the ore vein and not the host rock. And of course, we also want to identify the rock quality, and for example, to get to know where the fracture zones are. Second one is the predictive maintenance module. And with this module, we want to implement machine learning active processes. And this is done with, of course, AI algorithms from our Greece partner. And this development tool indicates and includes the automated machine learning and deep learning processes of the AI algorithms. And what we want to do with this is to get the actual equipment degradation and predict the future health status. And so on, we want to detect anomalies, we want to predict the wear of the drill bit, and to provide recommendations about maintenance actions in the future. Here you see the drill rig D110. It's a drill rig with core drilling machine for exploration, a small one from Sandvik. It's now 9 years old. And this summer, we added 5 different sensors to it. We added the displacement transducer to getting the borehole or drilling length and also the penetration speed of the drilling process. We added accelerometers to get the vibration of the drill rig. We added rotational speed sensors to get the drill rod speed. And we added 2 hydraulic sensors at the rotation unit and the chuck bar, and also temperature sensor for the hydraulic circuit fluid. Now I will get a deeper look inside the installation process. Here you see the displacement transducer, which is installed at the left side of the feeding unit. And this measures the rotating unit position, which is located with the second red spark. It's a magnetostatic measurement, and one big requirement for these measurements and for the sensors was that we don't do any structural changes to the machine. So we added this on top of the current machine, which is normally working, and now I want to transform this into a Miner 4.0 platform. The second one are the accelerometers. So the accelerometers are installed at the rotation unit, which clamps directly the drill rods so that we get the most information about our drilling process, which is down at the drill bit. But with our requirements that we want to use normal drill bits, we are not able to set sensors in the drill bit, which is normally way at measurement-wide drilling processes at production drilling for oil and gas, for example. But this is not a requirement for this project. The third sensor is the rotational speed sensor. It is included at the front of the rotation unit and installed at the red cover. So it's a bearingless inductive sensor. And in the middle of it, there is a POM disk, which we implemented. And in this POM disk, there are 6 different metal plates inserted, which gives the signal to the sensor with the we can measure it if there's metal plate or no metal. These are installed the temperature sensors and the pressure sensors. So this is directly installed at the control unit for the pressure sensors and directly in front of the radiator for the temperature sensors. But this is normal usage of sensors to be installed at the hydraulic circuit. Nothing special here. We are tried to use normal sensors, which you can buy all for digitization strategies. The sensors are not really used for grinding processes, but currently we are using this mine, and it's heavy-duty sensors. They are captured all from heavy materials, stainless steel materials. So we think in our mine and our old ore mine, where we will produce it, there will be no problems. We focus it. And this machine is installed at the research education mine at the Technical University Bergakademie Freiberg. So we as a university have our own mine with our own license to it. There we can do a lot of research and education projects in the underground. There is this machine installed, and there we currently drilling our ore mine to get data out of this drill rig. Here you see now an overview about the sensors and data acquisition system. So one requirement to the sensors was they need all an interface which we can read out with digitization strategies. So all the different sensors have different interfaces. For example, analog voltage interface and the current interface with 4 to 20 milliamps, for example. And all these interfaces will go inside our data acquisition system, which is a National Instruments basis, and then directly into the mini computer. And the mini computer is the overall central of our communication system in the mine. So there we get all the data together, we synchronize all the data, and then transmit it via the real-time data processing, Apache Kafka, to our big data platform and Dimitris Innovex company. And as we have also a backup file that if something happens, we can read the data out from the current situation. We drilled the first time 2 weeks ago now, and there's some small analysis here. At the left side, you see the borehole length on the top of the diagram and the rotational speed in the RPM. So the borehole length constraints very linear, so which is very good, and the rotational speed is also constant and drops a little bit down, but this is fine because the drilling length is increasing. And the penetration rate is waving a little bit. This comes that we adjusted the hydraulic pressure at the feed unit. So with more pressure at the feed unit, you get a higher penetration rate. But if you are drilling deeper, then you need more pressure to fix the drill rod into the drill run. So you can see there, if the red line, the hydraulic pressure feed unit increases, also the penetration rate increases, which is a good, similar to it. And at the right side, there you see the acceleration sensor, and you see X, Y, Z accelerations nearly all the same. And this is now a big overview about nearly 3 minutes of one drilling process, because we can drill only 30 centimeters in one time, and then afterwards we have to rebuild all the drill rods to get the drill core out of it and then drill the next 30 centimeters. And yes, the next steps are to analyze this data, get a deeper look inside, and yes, we will produce new data in the next weeks. This is now my first and also my last slide. Here it's the overview about all the digitization processes in our mine. And these steps, the sensors, data acquisition, data management, data storage, and data analysis are all the same for all digitization strategies. And this is a good ending for my point. And thank you for your attention, and Glück auf from Freiberg. Thank you very much.
Thank you, guys.
Thank you too.
For the job. Now we can move on to some of the Mentimeter questions.
Of course.
Ready to answer them?
Of course.
On behalf of the public. So, okay, let us move to the first question that we have. Would you like to read it out? Or?
I can read it, yeah, of course. What are your biggest challenges in digitization for your mining operation? So this is, for mining operators, a very important question where they are focused currently, and some points which projects we need at our universities, which are the focus to it, and let's see what the companies and the participants say about it.
Go ahead with answering the questions where we are waiting for your feedback.
Okay.
Yeah, okay. We got one of the first ones.
Let's hope to get other questions.
Before we move to another question, let's get some more answers here.
Yes.
Okay, first thoughts on the things that come here first as data management and analysis?
And my communication system. It's increasing. We're waiting 10 seconds, okay.
10 seconds, okay.
But the mine communication and data transport system and data management is on the top. So we are also in underground mining. In underground mining, communication system is always hard because you cannot use normal communication systems like here in the room. Okay. For wireless communication systems, the ranges are very, very low. And normally they use fiber optic wires to it, but the whole mine is every day increasing. So you have to install and get further the mining communication equipment, and this is very, very expensive. This is one of the most answered questions here, but this is really different I did this question to another set of presentations, okay. And there was the mine communication system, the 6th pass.
Okay.
Nobody had a problem with this. Nobody had a challenge to it, truly, but...
Depends who you ask.
It depends who you ask, and from my side, it's always a communication system, because you can generate data, you can analyze data. This is normally not the trickiest part from my side, but you have to transmit the data.
You have to still feed it back to the surface to get it analyzed. Okay, maybe then we can move on to the second question here that we have. In which areas do you see the greatest challenges of the mine of the future? That's some kind of what will come in the future, and waiting for your responses here. We made it already easier for you guys, you have to select one of 6 points, so go ahead, select 1 or 6 or whatever you fancy. Okay, mine communication is one of the first one that cropped up, so you made a good pep talk, Max.
Yeah, mine communication is always on the top also here.
But I see that also the autonomous navigation is rising. That can be also understood because it's also connected with the communication package. Yes, you cannot use GPS, you cannot use standard, GSM stations to localize you. So you have to need some fancy systems.
Correct, and it also figures out that what we are doing here. In our Portugal pilot site, we do their mine robotics, automation, navigation, with the underground robotic, yes.
Okay. Maybe we'll close this poll and move to the next question that we have here.
Please name your current digitization or digitalization projects.
Yeah, this is open question.
Open question. Put your words inside. What they are doing, what they are figuring out. We are very interested in it.
Maybe we can find some way of collaboration and to help you out. We are utilizing lots of stuff within the Mine.io, and only we have shown you just a tip of the iceberg that the guys are working here on the platform of Mine.io.
Yes, indeed. So, no response.
No project on digitization.
Maybe we could
maybe
move on and...
No, maybe it's easy.
Oh.
Depends who you ask.
Okay.
Microservices and IoT edge.
IoT as edge computing, maybe, yeah, or to analyze the data.
Yeah, and as the
Express schema validator. I'm not so sure about what's that meant.
I guess it has to do more with the interoperability aspect of the communication between diverse schemas and data sources and all of the stuff.
Okay, okay. Oh, okay, we got something more coming here.
security?
Yes, of course. Of course, security crosses the whole process of the data management. And for Mine.io as well, we have the security by design provided by Luleå University. So yes, it's a very, very significant aspect that we have to take into consideration.
Yeah, whenever there is data and there is transmission of the data, there's also a chance that basically it can be spooked or overheard or whatever.
For sure.
For sure, there is some kind of security.
For sure, it's a critical point.
Maybe we will go with the last question that we will have here.
Okay, which data management technology is likely to have the biggest impact on future mining? And we have, firstly, we would like to say that it's a ranking question and not a correct or wrong one. So we have the cloud storage and services, AI and ML, IoT devices, and edge computing.
Okay, AI and machine learning are growing, so probably.
Okay, I don't know what is the most significant. Of course, all of them play a key role in future mining. What would I say? I could say for the edge computing, it has to do with processing, data processing on the field. So we can have, let's say, a faster data streaming from the field to the respective platform. The AI and ML are responsible for sure for the predictive maintenance technology. So for sure it's very critical. The cloud services, the cloud storage services, of course, provide scalability, but okay, we have to deal with the security vulnerabilities and reliability, the data reliability, of course, since we have to manage the connectivity. And last but not least, the IoT devices. Okay, all of us know that they are responsible for providing data from the mining equipment to the edge computing. So I think that all plays a very critical role for the future mining.
Okay, thank you. Maybe we will stop here with this presentation. Thank you, guys.
Thank you. Thank you.
Thank you.
Maybe you should not run too far away because we have some
For sure.
package that basically is about open questions and open discussion. So if the viewers online would like to ask some questions, then please let us know through chat option, and we will run through those questions. We have noted some questions that appeared a few moments ago, and okay. The first question that I have here, the mining industry. The mining industry often refers to standard architecture. Have you used such standards? Questions like what is a mine, what is a life of a mine, and also important. So we don't have a colleague here, the representative of the standardization issues that we covered during the Mine I/O.
I think that it has to do with architecture.
But some architecture can be asked here.
For sure, we are affected by standardized mining architectures, such like Rami, like Cisco, and I don't remember the third one, but for sure the Cisco reference architecture and the Rami, for sure they were very useful for establishing the Mine I/O reference architecture.
Okay, I think that the next question is also directed to you because we have here the questions. I'm not so sure if coming slide will elaborate more on the use of ISO 10303, but I appreciated more details on how it is being utilized.
Okay, we were not the expertise in this ISO and the PLM module, but in the Mine I/O platform, cloud platform, we're going to use it as a storage solution for the use case in Freiburg. So the only detail I could provide at this stage is that we're going to utilize it as a storage solution.
Okay, great. There are a few more questions about the same ISO standard, so basically we'll answer them as a package.
Yes,
maybe later on.
Okay, but of course we're not the technology providers of this ISO, so for sure I do not have so many details. But okay, let's see at a later stage which is the questions, and maybe I could say some things.
Yeah, we'll directly answer them for the person that had that question. The next question is about muons. So it's to you, Mario. It's about the, as someone stated, it's that the telescope is efficient in the case when you have density, the difference in the density. But the question here that crops up is, can it be used in the case of rare minerals that occur in low concentration, ppm concentration grades?
Can it be used in the case of rare minerals and metals occur in ppm grades? Well, this is a good question, and I will say that is case dependent, because even if you have, these metals occur in a ppm grade, but is finely disseminated, and this relates to a rock that is finally more dense, even with ppm content, but if you sum up as a bulk, and it makes a density difference when compared to the host rock that is not mineralized, it can be measured, but also we'll need a trial. We will need to see how it compares. Perhaps the difference is too little. We know for sure that it works much better when the differences between densities are more evident when there's massive sulfides, for instance, compared to the host rock, which is a big difference in density. But in the case you mentioned, we will have to see how this relates to the host rock or unmineralized rock. Difference relates, right? So it's not about ppm, it's not about content, it relates about density comparison, I will say. Yep.
Okay. As we have Paula here on stage, the next question might be to you, because it's related to the underwater rovers. So, can the robot operate autonomously in an unknown environment, and how long can the mission last, and how long of a distance can the mission cover?
Sister Nun. Which robot are they talking about? But
not specific here.
Yes,
mentioned.
but both the robots that Mario presented, thank you for that, I'm so sorry. They can operate as an AUV, autonomous underwater vehicle. You just need to take off the cable. EVA is already very autonomous in that sense, and we are in this project enhancing the autonomy of Ushijun Neo, the round one. And it depends, the time that it can operate, it depends on the batteries. And usually for EVA, it can go up to 8 hours or a little bit more. It depends on the conditions, obviously. And it's the same case for Ushijun Neo. And the distance, well, the distance, it will depend also in the visibility, because if there is poor visibility, they will need to use the sonars to navigate, and they will use more battery. So I can't give you exact distance, but we know more or less the speed of the robot and the distance that it needs to cover, and he will need also battery life to come back. Yeah. So that is, it depends for each case.
Okay, so it's case dependent, it's not a straightforward answer.
Yes, but the batteries is more or less 8 hours, but we can push a little bit further, so.
Okay, is there a way to also to supply the robot with a cable and a power supply then? To act it in the more, or
no, but
the flooded mines are too complicated? In
case of Ushijun Neo, and it's one of the things that we are also doing in this project, the cage that is used to deploy the robot, it will have optical link for data transfer, but also we intend to check if we can charge the batteries.
Okay.
But that is not the case forever.
Okay, yeah, thank you for the answer.
Thank you.
Maybe one more question that we will cover the muons. What is the cost of muon sensors, and how many do a person need to install them to use them in an existing mine near the exploitation?
Okay, well, the cost itself of the device is not that much. It's mostly basic circuits and scintillators. What is costly is the development of it, right? So the research and developments and the years to make it functional, right? So we cannot say like a fixed price, and plus it's not the intention, but.
Should I move back to?
Okay, what was the other question?
And how
many needs to be installed if you want to use them in an existing mine for near mine exploration of possible unknown mineral deposits? With one muon detector, it's good enough, but it will be good to have several points where you can move it, right? So with one is enough, as long as you can have several point of views, right? Think that the muon detector acts as a telescope. So you can have another angle, then another angle, and start collecting different points. And then you get a more accurate image with more resolutions. And upon the objectives of the mine, if it's near exploration, it's enough. Even the probe detector, the one that goes into the drill holes, can be moved into several different holes, different positions, different depths, according to the objective.
Okay. The next question that I have is basically for Vasileios. How often do you need to make the drone flights to keep the risk assessment up to date?
Although this is more or less a question for my colleagues from USAL that they are dealing with mainly with the development of this kind of equipment, I may say from my knowledge that it depends on the results and depends on the complexity of each case. Maybe if you have to consider a case that, for example, you have only surface pollution, let's say in a pact of soil of a couple of centimeters, maybe 1 or 2 flights will be enough. But in case that we have complicated systems like the one in our repository, okay, or a great areas of contaminated sites, of course, this will be case-specific, of course, and we expect that we need much greater number of flights. For example, in Lavrion, we'll conclude the basic data management with the drone flights in almost 3 different field campaigns. Okay, so this is my answer, but also Christina from USAL may also give more technical details by email.
Okay. Basically, I see that some more questions are coming in. If we will not manage to answer all of them right away, we will try to get in contact with you guys through email. Maybe one more question that we have to Raul. Basically, the question would be, how do you decide where to place the sensors? Does it depend on the volume? What measures can you place more or less randomly? So basically about how to place the sensors, we have seen some pattern that you place the sensors, or so can you give us some insights on that?
Yeah, basically the sensors are distributed depending on the target. So there is some spatial resolution that we need to design. If we target on the depth, if we're working with tailings, typically tailings, they have these depths between 20 meters, 30 meters depth here in Europe, but not those tailings in America or in Australia where they can have hundreds of meters. So if we are targeting, for example, 20, 30 meters or a depth about 50 meters or 60 meters, we put sensors in an array every 5 meters or every 10 meters. If we want to target deeper, 100 meters, then we put more space in between the sensors. Now, the location is pretty much localized. We put the sensors above of the target. Yeah.
So it's far from anything that was mentioned as random. It's quite specific.
It's quite specific. It's
Okay.
quite specific.
Yeah. One of my last questions will be to Dimitris and Max. So how about the usage of this platform to other industries? So do you see the application of such platform and such things in other industry?
Yes, one of the requirements that we would like to meet with when designing the MineIO platform was the scalability. So we're providing the chance to for other cloud services to be integrated with the MineIO platform. And of course, we're providing someone who would like to adopt this solution, the whole solution of the MineIO. It will not need it to implement and develop a lot of connectors and in order to integrate with the MineIO platform. So in our mind was, when designing the platform, was to be scalable. So I think that this is an attribute that we're providing with the design of this platform.
So again, with some additional tweaks, you are able to let's say, more or less copy the platform and move to the other.
Yes.
Of course, there are some amendments needed because it's not only copy-paste.
Yes, of course, but of course, you are right, but this is our first approach. The scalability was one of the most critical aspects of the MineIO platform design.
Okay,
I don't know if Max would like something to add.
No, I think the question was really good answered, and you can change the platform to every digitization what you want. So we are doing drill rig, but you can also do some other machines that's not independent to this.
Yes, we would like to cover the heterogeneity of the MineIO pilots, and there is a huge heterogeneity between the pilots. So this is what we had in mind. So I think that this platform maybe could cover a lot of diverse pilot needs and requirements.
Okay, thank you.
Thank you.
Do we have any questions from our audience here in the room? Someone would like to answer, or you will have your time during the break here? If not the case, okay. Then we are coming to the end of the workshop. Thank you, first of all, for all the attendees, online and here on site, that you bear with us and stayed. Thank you for your interest in the workshop. The next is for sure coming in 2025, so apply on our media, social media, and also here you can see a QR code that we are waiting for your feedback. So of course it can be positive. We are basically very happy about positive feedback, but it also can be feedback that basically will allow us to build on that something, so basically and develop. So there are only 4 or 5 questions that will take you just a few more seconds. So please take a while to answer those. So big round of applause for the speakers. Thank you guys for preparing those presentations and being here. And one more thank you from me, from the guys that are behind the scenes and doing all the magic that happens afterwards. So tak so migen and dziękuję. Thank you guys.